So let's begin. Sorry about the noise in the background. I can't really stop that from happening. I think they're cutting down some trees near my apartment. Um, guys, sorry, but we're gonna have to keep learning during this time. I know that everybody's worried about getting a virus and stuff, and we're all supposed to stay at home, but that's no excuse for you to stay dumb. Okay. So today's topic is actually exponential functions. Okay, it is actually really relevant to what's happening right now because I'm pretty sure you guys have seen exponential functions on the TV whenever you watch the news, if you watch the news. But either way, it's pretty important to learn about these. Okay, so exponential functions, we're going to be talking about exponential growth functions. Well, before I start off with that, let's track back a little bit and talk about what an exponential function is. Okay, well, oops. An exponential function is an equation in the form y equals to a times b to the power of x, where a does not equal to 0, okay, and b is a value other than 1. Okay, also not usually equal to 0, but just, still just other than 1. Okay, whenever we have an exponential growth function, well, then a is actually going to be greater than 0 and b is going to be greater than 1. The function y equals a times b to the power of x, that's going to become an exponential growth function. And the value of b is actually going to be called the growth factor whenever it's greater than 1. Okay, it's growth factor because it's greater than 1. It means that your equation is going to increase as you go over to the right. But I'll show you that in a moment. Okay, the simplest form of an exponential growth function is actually just y equals to b to the power of x, with the same condition that b is going to be a value greater than 1. Okay. By the way, if you guys need to pause this at any moment, go ahead. You can read it out. Try to learn at your own pace. Okay. So you have as much time to go over this as you want. I'm gonna have very small assignments. That way, you guys aren't too stressed out about your grades and aren't too stressed out about not being able to complete the work. I will be normally on my computer in the mornings, probably from 12 to well, actually I'll be on there pretty constantly. So if you guys have any questions, you can go ask me a question on Remind. You can ask me a question on Microsoft Teams, and I should be able to answer you pretty quickly. If you need me to do anything one-on-one with you, then that's fine as well. I'll try to make video chats for everybody. This is going to be a lot like college, guys, so you're going to have to learn a lot on your own by going over stuff with me. But in case you have any questions, you have to come to me, email me, send me a message on Remind, send me a message on Microsoft Teams, sort of like office hours at college. Okay. Well, let's continue. Okay, so exponential growth functions, b is greater than 1, a is something other, just not equal to 0, sorry. And well, let's look at an exponential growth graph. Okay, so I'm gonna use a different color here. Let's say, yeah, I'm pretty partial to blue. Okay. Hopefully you can see that. These are going to be our x and y axis on the graph. Remember, this is our x, this is our y, and we are actually going to be graphing one of the simpler exponential growth functions. We'll say y equals 2 to the power of x. Okay, this is one of the simplest ones just because, well, it's just a small number and it shows like a growth rate, yeah, let's call it that. Okay, well, we'll start off by making a table of our values that we're going to be graphing. It should only be a few, but let's go ahead and do it anyways. Okay, so we have, I'm going to have -2, -1, 0, 1, and 2. Okay, when 2 is raised to the power of -2, this is actually equal to 0.25. When 2 is raised to the power of -1, this is equal to 0.5. Notice that these are not going to be negative values, even though we have a negative exponent. This is because the value actually turns into a fraction where we turn the exponent back into a positive value. Okay, so it becomes 1 divided by 2 to the power of 2, which 2 to the power of 2 is just equal to 4. So I'm going to write that down over here. 2 to the power of 1 equals to 2. And any value other than 0 raised to the power of 0, well, if you guessed it right, it is 1. Okay, now I'm going to go ahead and plot these down now. Okay, I'm going to start off with this one right here. X equals 2, y equals to 4. So 1, 2, and 2 to the right, and 4 up. Right there. That's going to be our first point. Okay, and then I'm just going to move up. 2 and 1. 1 and 2. X equals 1, y equals to 2. X equals 0, y equals to 1 is right here. X equals -1 and y equals to 1/2 is right here. You see that's halfway through, or halfway up. X equals -2 and y equals to 0.25. 0.25 is just a quarter. So that's 1/4 of the way up. So it looks like this. Okay, now we do have values in between, but we're just going to go ahead and connect the points. If you notice right here, what's happening here is that the values are increasing by doubling. Okay, this is a doubling equation. So you see 1/4 turned into 1/2 because 2 quarters make 50 cents. And then if you double that, 50 cents make $1. If you double that, $1 makes $2. Doubling $2 will give you $4, and doubling $4 would give you $8. So this point would actually go right there. Okay, now if you go backwards, the same thing happens. You half the value. Yeah. But I'm just gonna go ahead and finish off that graph by connecting the points. Oops, I'm a little bit off there. Oops. Let me try to erase a little bit. All right. Okay. Now, damn it. Sorry. Yeah, now, we have another important thing that's happening here. Okay, now, because we're halving the distance, or not the distance, the value, there's always going to be a value in between the current value that you're on and the value 0. Because no matter how many times you halve anything, you're never really going to reach the value 0. So this equation, this function or graph, is actually going to have an asymptote right here. It is green one. At y equals to 0. This can change depending on what the graph looks like, but basically you're always going to have that line that it's never going to cross. So the red line only stays on top of that green line. Okay? Only whenever it's exponential growth, though. Whenever it's exponential, other different types of exponential functions that might change. It might just be flipped over, or it might be mirrored, but it'll look something like this regardless. Okay. I'm going to go ahead and move on. Okay, so next up, we have applications of exponential growth. This is basically the types of problems that you guys are going to be looking at. Okay, so when a real-world quantity increases by a fixed % each year, or this could be another unit of time, it could be a day, it could be an hour, a minute, a week, a month, a decade, a millennium, or a century. Basically it doesn't matter. It's just a unit of time, right? Like they go up by like 10% in a day, 10% in a year, whatever. The new increased quantity can be modeled by the equation. Well, let me write this down actually, because let me do this in black. Okay, it's going to be the equation y equals a times 1 plus r to the power of t. Okay, and y is going to be equal to the final amount. A is going to be equal to the initial quantity. R, this R right here, this is actually going to be the percent increase as a decimal. Okay, and then T is going to be the amount of time or whatever unit of time that you wanted it to happen. Let me go ahead and move on to the next one. Okay, so here R is just the decimal format of the percent increase. 1 plus R is the growth factor. Yes, so I didn't mention that earlier, but earlier I said I think B or base is the growth factor. Well, whenever you have applications, they're going to give you a percentage, and you're always going to have to add 1 onto it in order to see your growth factor. Okay, A is going to be the initial starting quantity. Maybe I should write down the other ones. I don't think I added those. T is just the amount of time that happens. That passes. Okay, so if it's like, if they say it's R% each year, and they want you to, they ask for what's the new quantity in 2 years, then your T will become 2. But if they say what's the a final quantity after a decade, well, then you have to think, well, how many years are in a decade? There's 10 years in a decade, so well, that T would change into a 10 instead of a 1 for years, right? Okay, and I think that's it. I guess I'll just add that y is your final value. Okay, and then we'll move on. Okay, let's try some problems out actually. Okay, so here's an example problem. Let's say the number of penguins in Antarctica increases by 5% every year. In 2019, the penguin population was 1,250. And it asks, how many penguins will there be in 2020? Okay, well, if we go back, we can copy down our format, where we're going to have y equals to 1 plus r to the power of t. Okay, so y equals your initial value, which the initial value in 2019, that's your population of penguins, that's 1,250. Our growth rate is going to be 1 plus our percent increase, but the percent increase has to be written down as a decimal. Okay, this is the easiest way of getting that decimal. Getting that decimal, turning that percentage 5, and then dividing it by 100. Okay, this is just in case you don't know how to do it. Okay, this turns into 0.05, and that's actually what you're going to be adding over here. Okay, and it says how many penguins will there be in 2020? Okay, well, this is the population in 2019. So in 2020, 1 year has passed. So we're gonna say power of 1 right here. Okay, so that's 1250 times 1.05. That's some quick math for you. Just add the 1 and the 0.05, you get 1.05, and to the power of 1. Okay, the power of 1 is kind of obvious. It just means that you're going to have to multiply times 1.05 by itself without the exponent. but if it helps you remember that you're going to need an exponent there, just write it down every time. Okay, so what I'm getting here is 1312.5. Okay, so I would probably approximate this. Okay, so we can't really have half a penguin, so I'm gonna say 1313. Okay, that's how many penguins there would probably be in 2020. Okay, now it says how many penguins will there be in 2022. Okay, so 2022 is 3 years after 2019. So since we changed the 1 for 1 year after 2019, we can change the 1 into a 3 for 3 years after 2019. Okay, everything else stays the same though. Okay, 1 plus 0.05 power of 3. Okay, so again, that 3 is because 2022 minus 2019 equals to 3. Okay, that's the only reason I'm using 3 now. Okay, and you can use like if you're getting confused by that, just remember it's just a number of years. Okay, it increases by 5% every year. So in 3 years, it's going to increase by 5% 3 times. So 1 plus 0.05 to the power of 3 is what we want to write down there. And then we just multiply. Okay, so we have 1250 times 1.05 to the power of 3. Okay. What I get here is actually going to be 1447.03 approximately, I think. Yep, and it's an approximation. I think the rest of the values are 125. Okay, but this is a really small decimal. It's much less than 0.5. So I'm actually going to be rounding this number down for the new population. So I'm going to say 1447 penguins. Okay. Yeah, so 1,447 penguins is the population in 2022. The next problem is going to be a money problem. It's also going to be a pretty good example of what something you might want to learn for in the future in case you're an accountant or just anybody who deals with money, really. Okay, if you're trying to retire, you definitely want to know about interest rates. Okay, so let's look at the next problem. Okay, so suppose you have a savings account where you receive interest on the current balance. Initially, you start off with $5,000 in the account and receive 2% interest per year. What would be your balance at the end of 3 years? Oh, first of all, let me explain this again, or for you guys. Whenever you have a savings account, they give you interest. This means that they give you money in return for letting them keep your money in a savings account. So it's sort of like they're paying rent for your money in a way. But it's actually much more beneficial for the banks to keep money like that. That's why they give you a small amount of money, because in the end they'll be making a lot more than you would spending it. I guess they'll be making a lot more than what they pay you in interest. But that's for your economics class. Let's talk about this. Okay, so again, initially you start off with $5,000 in the account and receive 2% interest per year. What would your balance be at the end of 3 years? Well, we're gonna go ahead and start it off with y equals a times 1 plus r to the power of t. Okay, a is our initial amount, which in this case is $5,000. Okay, 1 plus r is going to be 1 plus your percentage, your interest, your growth rate, well, your growth, written down as a decimal. Okay, 2%. Whenever you divide it by 100, gives you 0.02. So you write down 0.02 right here. Okay, and then we raise it to power of t, which is the number of years you want to leave this money in there for. So that would be 3 years. Okay, this is pretty easy. But you know what? I'm gonna make this a little bit slower, just so that you guys can see how this is growing. Okay, so this is actually a thing called compound interest. Okay? I didn't make a slide for this, but I want to talk about it anyways. So compound interest means that you're going to be gaining interest on an amount that you originally had, and then as time goes by, you gain more interest because your value keeps increasing. That might not make sense as much at a first glance, but let's look at it this way. Okay, so with compound interest, you have $5,000. Okay, and after 1 year, you increase that value by 2%. So that means that you're going to be multiplying that value by 1 plus 0.02. Okay, you can raise it to the power of 1, but it's not really necessary. Okay, so 5,000 times 1.02 is going to give us 5,100. Okay, now you have a different amount in your account after 1 year. Okay, for your second year, you're going to be gaining interest on that amount, not the original 5,000. So you're not just going to get $100 back, you're actually going to gain a little bit more. So I'm going to take 5,100 and I'm going to multiply by 1.02 again. Okay, so 5,100 times 1 plus 0.02 to the power of 1. This is one more extra year, and that's going to give us $5,202, which is pretty crazy. You know, you gained $100 the first year, and then you gained $102 the second year. See, so you're increasing your interest by a little bit more. All right, but this is 3 years, so we're going to have to do one more year. 5,202 gets increased by 1 plus 0.02 to the power of 1 because it's only one more year. And this time we are going to gain slightly a little bit more, and the amount is going to be $5,306 with 40 cents. Okay, so you actually ended up getting quite a bit more this time. You ended up getting $104 with 40 cents. Okay, so that might not seem like very much, but over time this can keep adding up and keep adding up and keep adding up, and eventually you grow to have a lot of money from just a small amount. Of course, this is a really slow growth. Okay, if we go back to the doubling equation, let me see. Okay, right here, you see how right here in this part, it's pretty flat. But then at one point, which I would probably say right around here, the equation starts growing pretty quickly. You see how it starts becoming more and more steep. So at the beginning, it's pretty flat. It's almost like that, right? And then it goes like this. And then it's almost vertical, meaning that it's almost increasing like by a lot more, almost infinitely. But it, you know, that's not really actually going to happen. But let me go back. Okay, there we go. Okay, so yeah, you can start off with a little bit of money, like a few cents, and then over time, if you wait long enough, if you have the right percentage, eventually it becomes a lot bigger. Okay, now, so our answer for this problem was actually going to be 5,306 with 40 cents. But let me try it this way too, just to make sure. So 5,000 times 1 plus 0.02, which is just 1.02 to the power of 3. And actually we got the same exact answer, which is pretty nice because that means whether you do it one way or you do it the other, you're still going to get the right answer. Yeah, and that's what's so fun about math. You can get to the right answer in so many different ways. Okay. All right. So this is a different type of problem that I also want to go over. You guys have already gone over these, but now we actually have a small application. Okay, so it's the same type of problem. Suppose you have a savings account where you receive interest on the current balance. Initially, you start off with $5,000 in the account and receive 2% interest per year. How long would it take to double your money? Okay, well, double your money. You start off with $5,000 and you want to double it, so 5,000 times 2 will be $10,000. So 10,000. Okay, and we're going to be using the same format again. Okay. So 10,000, that's our final value, equals to our initial value, 5,000, times 1 plus r, 1 plus 0.02. Okay, because remember the interest rate is 2%, just like before. We're still using the same r. And we're going to raise it to the power of t. Okay, it says how long would it take for you to double your money? Well, what we're trying to find here is actually the time. We're trying to find, give me a sec. Let me highlight it actually. This value right here. Okay. We're trying to find out that time that it will take for you to double the money. Okay, but we've already done this before. Okay, yeah, it's like you guys have done in class. You guys did a really good job of doing that. Actually, we're going to take the 5,000. Okay, we want to get, well, let's add the exponent, the base first. 1.02 to the power of t. 5,000 goes over here on the outside, and it still equals to 10,000. I'm not changing it, the equation. I'm just changing the way it looks. Okay, but now I'm actually going to try to solve it. Okay, so we want the base and the exponent to be by itself. Okay, we need to figure out what that value of t is. So we're actually going to be using logarithms here, which, remember, they're really useful. I'm going to take 5,000. I'm going to divide it on both sides. Okay, this 5,000 is going to go away because 5,000 divided by 5,000 equals to 1. And basically 1 multiplied onto anything else is going to give you the same value. So it just goes away. It reduces itself. Okay, now 10,000 divided by 5,000, well, that's equal to 2. So 1.02. You don't really need the parentheses here, so I'm just going to not write it down. But if you want to have it there, you can. Doesn't quite matter. Okay, so we have 2 equals to 1.02 to the power of t. Okay, now I need to get that t value, so I'm going to move it down to the bottom by taking the log of both sides of the equation. So I'm going to take the log of 2. I'm going to take the log of 1.02 power of t. And what this is going to do is that it moves the t over to the bottom in front of the log, and it still stays the same. Okay. Next up is getting the t by itself. If I take the t, well, the side with the t, and I divide both sides by the log of 1.02, divide by log of 1.02 over here too. These logs are going to reduce each other, and then we're going to have t by itself. So I'm going to go ahead and write down my answer over here. Log of 2 divided by log of 1.02. Okay, so I know that you guys are going to have some problems trying to figure out, well, you don't have calculators with you. Okay, you can try using your phone, you can try using the internet. If you can't have either one of those, for my homework, Oh, well, yes, there is going to be homework. I want you guys to just leave it like this. Okay, this is fine. Like I know what this value means. I know that this is going to be your final answer. If you want to leave it like that, that's fine. If you want to leave it as an actual value to check your answer, that's fine too. Okay, so I'm gonna give you the actual value here. Let's see how much time it takes for you to double your money. Let's see. So log of 2 divided by the log of 1.02. And that's approximately 35. Whoops. What the heck? Well, sorry, I think my pen ran out of battery. But that's fine. T is approximately 35. Let me see if I can get this with my finger. Okay. Yeah, so, sorry. My pen ran out of battery. So let me charge it. But yeah, T is approximately 35.003. But basically, it takes 35 years for you to double your money this way. But anyway, that's how you want to solve that type of problem. Let's look at what's next. Sorry. Okay, so suppose you have a savings account. Okay, so the same type of problem. Okay, and it says how long would it take for you to have a balance of $7,000? Okay, so here the same thing happens. I'm gonna look back and you see we wanted to double our money, but now instead of doubling, we're actually gonna want to make it $7,000. So I'm going to go ahead and write that down. 7,000. Whoops. What did I do? $7,000 equals the original $5,000 times 1 plus 0.02. Okay, I'm using the same interest rate, so therefore we have the same decimal. And then to the power of t, because we do not know how much time this is going to take. Yeah. Just like before, I'm going to divide both sides by 5,000. Okay, we want the exponent to be by itself. Oops, 5,000. I'm going to divide by 5,000 on this side too, because equations have to be equal to each other. Okay, so whatever you do on the one side, you have to balance it out on the other side as well. Okay, it's just like a scale, you know, like if you take a weight off one side, you got to take it off the other side, otherwise it becomes unbalanced and therefore not equal. Okay, so the 5,000s cancel out. 7,000 divided by 5,000. Let's see how much that is. Oh, that's 1.4. Damn it. Sorry. 1.4. Let me erase that. Sorry about this, guys. It's an inconvenience, I know. $1.4 right there. Okay, on this side, we still have 1.02 to the power of t. And we're going to be doing the same thing as we did earlier. We're going to take the log of both sides. Log of 1.4 equals to the log of 1.02 to the power of t. Okay, the t is going to move over to the front of that log, and they are still going to be equal to each other. And then on the other side, we have log of 1.4 still. To get the t by itself, we divide both sides by the log of 1.02. Divide by the log of 1.02 on this side. And once we divide both sides by log of 1.02, those logs cancel. And then whenever you actually divide this, you put this into a calculator, or you can leave it like this if you don't have one. Sorry, I'm messing around with my calculator. Once you divide them, you actually get 16.99 equals to t, meaning that it would take you almost 17 years for you to get $2,000 with that interest rate. Okay, so let me put that. Yeah, that's supposed to be an S, but yeah, there we go. 16.99 years is your T in order for you to have a balance of $7,000. Let me go back. The same thing over here. This one was 35 years, which is a pretty long time. Pretty long time. Okay, but hopefully with these examples you're able to do the next two problems. Okay, now this is going to be your classwork. I will create an assignment online. Actually, how do I want to do this? You know what? So you could do this in a few different ways. I want you guys to do these problems. Send me a picture of your work. Okay, just your work and your final answer. Okay, you can send me a picture through Remind. That's the best way possible. Or you can send it to me through the Hub or even Microsoft Teams. You guys are all added on your classes, so send it to me through a message directly to me, and then in a few days I will be posting up the answers just to make sure that you guys have them corrected. If you got it incorrect, then just look at the answers and send me a new message where you tell me, okay, this is what I did wrong. Okay, but let me show you guys the work. Okay, so this is problem number 1. I'm gonna leave this up for a few seconds. Make sure to pause the problem, pause the video, in order for you to be able to see this. Alright, and then problem number 2. Okay, now remember, send me a message on Remind with your answers. Okay, take a picture of them. Make sure to block them. Make sure that it's visible. If I can't see it, I can't grade it. Okay. Alright. So, good luck, guys. I will be posting probably around every other day. That way you guys aren't too stressed out by all the work. I know that all your other classes are going to be doing a lot of work. I'm trying to minimize this for you guys, but we have to learn something. Okay, next year is approaching. I know that you guys aren't going to have to worry about any STAR testing anymore, but you might have to take it next year. I don't know. I don't know how that's going to work out, honestly. But, yeah, that's it. Goodbye. Take care.